Welcome to this lecture series in coordinate geometry. In this lecture, we'll learn about half planes, and all we need to know is basically what is the equation of a line, what does it mean to write down something like this, 2x plus y minus 3 equals 0, what is it trying to capture, etc. That's all. Here are some problems for practice. And now let us get started. So we have the coordinate plane, and I have made this particular line, which is 2y minus x minus 2 equals 0. Right? This line has a point, let's say, so even before I talk about this particular line, suppose I have any line on the coordinate plane, or in the Euclidean plane more precisely. So I have some line somewhere. Clearly, we have an intuitive idea of what are half planes. So this region is one half, this region is the other half, and this is the line. So how do we capture, geometrically speaking, the half planes? So you declare that 2 points A and B are on the same side if the line segment joining them does not intersect the line. So A and B are on the same side of the line if the line segment joining them does not intersect the line, and they are on the opposite sides of the line if the line segments joining them, or line segment joining them, is intersecting the line. So this is how you define opposite side and the same side, and it turns out that if you have 2 points, either they will be on the same side or they will be on opposite sides, obviously. Either the line segment will intersect or the line segment will not intersect. Okay, fine. Interestingly, suppose A and B are on the same side of the line and B and C are on the same side of the line. Then A and C are also on the same side of the line. This is intuitively obvious. So if this doesn't intersect the line, that doesn't intersect the line, then this will also not intersect the line, and similarly. So one can geometrically define this idea of half planes, but we are trying to capture it algebraically, so let's do that. All right, so before I write down the way to capture it, let us get a feel for it. So this line has a point, let's say, I think maybe you can take whichever point you like, but I just want to choose one point. So let's say y equals 1, then let's say y equals 2, then x becomes 2. So 2 comma 2 is a point on this line. I hope it is. Right. So this is on the line. Okay. And now let us isolate the expression of the line. The expression is this: 2y minus x minus 2. The points which make this 0 are precisely the points which lie on the line. But now, one such point is 2 comma 2. What happens if we substitute any of these points? Any of the points where x is 2 but y is something else. So either you can go up or you can go down. So suppose we go up. So here we are recording the value 0, but as we go up, x remains what it was, but y increases, and hence this must also increase. So this will take positive value on everything above the point and on this vertical line, and this will take negative value everywhere here. Okay, and this story is the same for every point. If we had started with some other point, all the points above will take positive value, all the points below will take negative value on this. Or rather, this will take positive value on all these points and negative value on all those points. So we are seeing that everywhere here, this guy takes positive value, and everywhere here, this guy takes negative value. Why is that? You pick a point, arbitrary point here, you come down, vertically down. At some point you will hit the line. Here you are taking the value 0, but there the x-coordinate remains the same as the one, the x-coordinate of this point is same as the x-coordinate of that point, but the y-coordinate is more. So this is more than 0. If this were taking the value 0 here, then it will take more value above. I hope this was clear. I smudged it a little bit, but basically that is the idea. So to capture half planes algebraically, suppose we are given some line. If our line is ax plus by plus c equals 0, one half side is where this expression takes positive value, and the other half side is where this expression takes negative value. Those are the half planes. As simple as that. No mystery here. And with that, let us just look at one example so that we can digest it. So here is the example. We want to find all values of alpha such that this point, this is a point on the coordinate plane now. Once alpha is a real number, this is a point on the coordinate plane. So we want to detect or determine all values of alpha for which this point lies inside the triangle formed by these three lines. So those three lines have been drawn here fairly accurately. Of course, it's not completely accurate. I didn't even try, but fairly accurately. And we want to find all the alphas for which this lies in this region. Okay. And if you just think about it, as you vary alpha over all the real numbers, what curve does this trace? This will trace a curve like this, something like that. I mean, it will be symmetric about the y-axis, maybe something like that. Okay. So to solve this problem, we do not need to make a diagram, but I have made a diagram just for illustration. So fine. So let's first find all the three vertices of this triangle. So to find A, we will simultaneously solve this with that. So these are two equations in two variables. If we solve it, we will find that this is the point of intersection. So this point has those coordinates. Similarly, B has these coordinates and C has these coordinates. These are the coordinates. And now, suppose we have a point P inside here. Let's say P is alpha comma alpha square. Or let's not say it is inside. It is somewhere. It is alpha comma alpha square. Now, how do we capture the fact that P is inside this triangle? So the main idea is, first let us talk about this line BC, and the point P is, if it is inside the triangle, it is necessary that it is on the same side of this line as A, right? So whichever side A has, the same side P has. Similarly, with respect to this line, whichever side C is on, the same side P is on, and whichever side of this line B is on, the same side P is on. Only then, I mean, this is necessary for the point P to lie inside the triangle, and this is also sufficient. So a point P, what I'm saying is a point P lies inside the triangle ABC if it is on the same side of any of the lines. Suppose you fix this line, then it should be on the same side as the opposite vertex. Same side as the opposite vertex, same side as the opposite vertex. So if it is the case that it is on the same side as the opposite vertex of any chosen line, then it is inside the triangle, and it is only when this condition is satisfied that it is inside the triangle. So just realize this fact. And that converts the problem into a purely algebraic problem. One other way to solve it would be to use this diagram. You could say that, well, the origin should be on the same side of any of the three lines. What I'm trying to say is, suppose you have a point P, then point P should be on the same side as the origin for this line, same side as the origin for this line, and different side as the origin for this line. So you can perhaps do it that way. But that requires you to look at this figure. We do not want to look at the figure in order to solve an algebra problem. Coordinate geometry is the algebra of geometry. So as long as possible, as far as possible, we should not rely on figures. And this solution has nothing to do with figures. You just solve these blindly, and then you just use the fact that the point P, meaning alpha comma alpha square, should give you the same sign as the point A gives you on this line, as the point B gives you on this line, as the point C gives you on this line. That's all. So let's first talk about point A. What is the sign that point A gives on this line? The sign that it gives is, what is the line? The line is that, so the sign we get is 1 by 3 in place of x, 1 by 9 in place of y, minus 3. So this is equal to 5 by 9 minus 3, which is negative. And therefore, alpha comma alpha square should also fetch negative sign. So therefore, alpha in place of x, alpha square in place of y, minus 3 should be negative. Right? This is what we get from point A. Using point B, we will be looking at line AC. And what is the sign that point B gives on this expression, this one? 5 by 4 in place of x and 7 by 8 in place of y. 5 by 4 comes from here, 7 by 8 comes from there, and we have a minus 1. So this is equal to 20 by 8 plus 21 by 8 minus 1, which is positive. So if we put alpha in place of x and alpha square in place of y, we should get positive sign. Right? So that's one thing. And lastly, for the point C, whatever sign it gives on this line, the same sign point P should give. So let's find the sign. Substituting minus 7 in place of x, 5 in place of y, this is equal to minus 35, minus 30, minus 1, which is of course negative. So if we substitute alpha in place of x, alpha square in place of y, minus 1, this should be negative. All right, so as long as these three conditions are satisfied, the point will be inside the triangle. And if the point is inside the triangle, these three will be satisfied. So this is exactly what we need to characterize. And now this is a question of quadratic equations. So maybe just give me a little bit of space. So when is this expression negative? It's a question of finding roots. Find the roots of this guy. The roots of this guy are, I think, if you calculate, the roots of this guy are minus 3 by 2 and 1. I pre-computed this. So for this to be negative, if you know a little bit about quadratic equations, alpha must lie. And this happens if and only if alpha is in this interval, minus 3 by 2. Let me not use interval notation because one may confuse it with coordinate notation. So it should be between minus 3 by 2 and 1, somewhere here. Maybe something like that. So that is the 0. So this is the region where the first inequality is satisfied. For the second one, the roots are minus 1 and 1 by 3. So what is the region where this is satisfied? This is satisfied in the region, we are taking positive sign. So less than minus 1. Here is where we have minus 1. This is 0. This is 1. This is 1 by 3. So in this region, greater than 1 by 3 and less than minus 1, that region. And similarly, here the roots are, for the last quadratic, the roots are 1 by 3 and 1 by 2. And since we are talking about negative sign, this happens when you are between 1 by 3 and 1 by 2. So 1 by 3 and 1 by 2. This is where this is satisfied. So ultimately, if you just work this out, if you take the intersection of all the three regions that you get here, you will see that sorry, we are taking negative sign. So, oh, no. Sorry, I said something incorrect here. So the roots are 1 by 3 and 1 by 2, but this the dominant term also comes with a negative sign. So it's better to write this inequality as follows. Let me just flip the signs. We flip the signs and we do this. Okay. Now the roots are 1 by 3 and 1 by 2. So the regions where this will be positive is greater than the bigger one, which is half, and less than 1 by 3. So that is the region where this happens. So this somewhere here is 1 by 2, greater than that, and less than 1 by 3. Okay, it's a little bit cumbersome the way I have done it, but I'm sure you were able to follow. So if you take the intersection of all these three regions, you will see the answer is in the interval notation. Alpha should lie in this open interval union this open interval. This is where alpha should lie. Precisely this is when, this point lies inside the triangle, meaning it comes here one time here and then the second time here. So that's how it kind of looks like. Okay. So I hope you were able to appreciate the notion of half planes. And with that, I want to end this lecture. As usual, like, comment, share, subscribe, and I will see you next time.